Welcome to our review for Practice Exam 2. First here we are looking at some short answer questions for integrals. We just want to state the method, and then if that method requires a substitution, state the substitution. If it doesn't need a substitution, then you're just stating the method. So let's take a look here at our study guide real quick and just kind of remind ourselves what the different methods are and the clues of when you use those methods. So here's our study guide, and if you scroll down here, you'll see this section, what method do I use? So some hints here. Well, first of all, you want to take and simplify the integrand, the function that you're integrating, or change its form, because that's going to help you try and determine which method you need. And then start with the easy stuff. So first look for a use substitution. See if you can use a use substitution. And if that doesn't work, start to classify your integrand. If you see a polynomial or a power of x times an e to the x, or times cosine x, or a log function, that's going to be your hint to try integration by parts. So things like x e to the x or x cosine x. If you've got a rational function, that's a polynomial divided by a polynomial, that's a clue for partial fractions. If you got products of sines and cosines or tangents and secants, then you're looking at a trig integral. And then if you've got underneath the square root, if you've got either x squared or an expression squared plus or minus a number squared, then you're looking at a trig substitution. And if underneath the square root you've just got like x to the first power, or sometimes an x cubed under there, or sometimes you have more than one square root, then you're looking at rationalizing substitution. And then sometimes you have to go back and you have to use more than one method. So sometimes you'll use a use sub to simplify the integral, and then you'll be able to go back and do another method to finish up. So for example, I look at this first problem and I see that root x minus 1, and it's not squared. Okay, so that is telling me that we should try and use a rationalizing substitution rather than a trig sub. So this is going to be rationalizing. And since rationalizing does involve a substitution, we have to tell what u equals. And usually u is going to be everything that's under the square root and including the square root. So u equals root x minus 1. And that's all the farther you have to go. Here I see a power of x times a transcendental function, log x. Okay, so that's going to be integration by parts. And then usually you are going to let u be the part that has the power in it. But there's one exception. With the log function, if it involves the log function, you want to let that be your u, because that simplifies when you differentiate it. You want u to be simpler when you differentiate. Well, both of these guys will simplify. The x squared will simplify down to 2x, and the log x will simplify to 1 over x. But the log x simplifies more. And then you want the dv to be easy to integrate. So, well, we can't integrate log x without another integration by parts. You got to let the dv include the 5x squared. So here we only need to specify what the u is, because the dv will be the rest. So the u is going to be ln of x. Okay, now if it was x squared e to the x, then the u would be the 5x squared. And then here we've got a x squared cosine of x cubed. And first you look at that and you think, oh, that's going to be another integration by parts here, because you got a power times a trig function. Okay, but notice here we got an x cubed and here's an x squared on the outside. So I see a function and its derivative. So this is just going to be a regular u substitution to start with. And you would let u equal the inside here, x cubed. And then if you do that, the du is going to have a 3x squared, and that's going to take up the x squared. And then it's just going to be integral of cosine u. So you don't want to work harder than you have to. On number 4 here, we got a square root, and I see an x squared in there, and I see a 4, which is also a perfect square. So this one's going to be a trig substitution because it's got the squares. And with the trig substitutions, remember what you do is you're trying to fit it to an identity here. So the x squared minus 4, that looks like secant squared minus 1. So your x squared minus 4 corresponds to a secant squared theta minus 1. Okay, those look alike. Okay, and then we want to match up the numerical parts here. Okay, so, well, this is a 1. We'd like to have a 4. So multiply through by 4. Okay, then your x squared plus 4, I'm sorry, minus 4, is going to be equal to 4 secant squared theta minus 4. So I just multiplied through by 4 so that these parts match up. And then that means that these parts have to match up. So your x squared is going to be 4 secant squared. So x is going to be square root of 4 is 2, square root of secant squared is secant theta. So there's your substitution, 2 secant theta. And then on number 5, and you don't have to do anything else there. Just state the substitution. Number 5, we got powers of tangents and secants. That is going to be a trig integral, which is a special type of substitution. So trig integral is powers of trig functions. And if there's, here we see there's an even number of secants. And remember, the derivative of tangent is secant. So the secant squared x dx, that's actually going to be your du. Remember, a lot of times with trig integrals, you look for your du first. And if the secant squared your du, then u is going to be tangent x. This will be u cubed. So it'll be u cubed du. So we're just stating u. So u is going to be tan x. And that one's done. And then number 6 here, we see polynomial on the top, polynomial on the bottom. That is going to be partial fractions. And that does not involve a substitution, so we just state that it's partial fractions and we're done. Now, just for practice here, let's look at what the partial fraction decomposition would be. Well, actually here, if we multiply this out on the bottom, we'll have an x squared and we get an x squared on the top. So the first step there would be to do long division. And then what's left is going to, so you do long division first. You don't need to write this down, but I'm just trying to give you some insight. So you long divide first, and then what's left, you're going to have a term on the bottom to go with the x minus 1, and plus you're going to have a term on the bottom to go with the x plus 1. And since these are linear on the bottom, it's just going to be numbers on the top. So a over x minus 1 plus b over x plus 1 is going to be the form of the partial fractions. Now again, on this one, you could just stop here. Okay, so that's the short answer. And then the next section, you're going to be actually working out the integrals. So here I'm saying, evaluate 5 of the following 6. So there's some choices in there. And I will give you choices on the actual in-class exam also. So in this question, I look at this and I see a polynomial on the top and a polynomial on the bottom. So I'm thinking, aha, we need to do partial fractions on this thing. Okay, so we need to do a partial fraction decomposition. So the first step of doing that is to factor the bottom here. So notice we've got a common factor of x. So we can factor out an x. And there will be an x squared left here. And factor an x out of there. Minus 9 is left. And then this will factor into x times, FOIL backwards on this. This is difference of 2 squares. So that's actually going to be x minus 3 times x plus 3. So then our partial fraction decomposition, this is going to break up. And we've got 3 linear factors. So it's going to be a number over x. And then it's going to be plus a number over x minus 3, and then plus a number over x plus 3. And we need to find out what those numbers are. So let's go ahead and find out the decomposition down here. So the partial fraction decomposition, this left-hand side, which is your 2x minus 3 over, I'm going to write the factored form here. And actually, let me move this over a little bit. Over your x plus 3, x minus 3. That is going to equal a number over x, we'll call it a, plus a number, we'll call it b, over x minus 3, and then plus another number, we'll call it c, over x plus 3. So remember, the only time that you have x's in the numerator is if you've got an irreducible quadratic in the bottom, like x squared plus 1. So then remember, what we do is we multiply to clear out fractions. We multiply through by the denominator on both sides. So we're going to multiply both sides by x times x plus 3 times x minus 3 on the right and then also on the left. So x minus 3 and x plus 3. Now on the left hand side, that just cancels out the denominator, and that just leaves us 2x minus 3. On the right hand side, we need to multiply this in times each term. Need to distribute that baby. And then part of it cancels with each one. So when we multiply this in times the a over x, then this x is going to cancel with that x. So we're going to have the a left on top. So it's equal a. And then we'll have the x plus 3, x minus 3. And then when we multiply this whole thing in times the b, the x minus 3 is going to cancel this x minus 3. So we're just going to have x and x plus 3 left along with that b. So plus b times x plus 3. And then when we multiply this guy in times the last term, the x plus 3's are going to cancel. We'll have an x and x minus 3 and that c left. So c x minus 3. So then remember what you do if you've got linear factors, you just start picking some numbers for x and plug in and you'll get 3 equations and 3 unknowns. So remember, the numbers, nice numbers to pick are the denominators in there. So we are going to want to pick x equals 0 here. And you plug that in on the left. 2 times 0 minus 3 is going to be equal to negative 3. And you plug that in on the right. And so you're going to get a times 0 plus 3 times 0 minus 3. So 3 times negative 3, negative 9, so negative 9a. And then when you plug the 0 in here, you get b times 0 plus 3. Well, that's just going to drop out. And then c times 0 minus 3, that's going to drop out. So we just have negative 3 equals negative 9a. So divide both sides by negative 9. And that's going to tell us that our a is going to equal negative 3 over negative 9, which is 1/3. And then we'll pick x equals 3. So plug in x equals 3 on the left and the right. So 2 times 3 is 6, minus 3 is 3 on the left-hand side. And then when you plug the 3 in here, you get 3 minus 3, that's a 0. So this term's going to drop out on the right. And then here, b times 3 plus 3. So that's going to be 3 times 6, 18. So 18b. And then when you plug the 3 in here, you get 3 minus 3, which is 0. So that term drops out. So we just get 3 equals 18b, and then divide both sides by 18. So your b is going to be 3 over 18, or 1/6. So the 1/6 is going to go over the x minus 3. And then plug in x equals negative 3. So x is negative 3. Plug that guy in. 2 times negative 3 is negative 6. minus 3 is negative 9. And then on the right hand side, if you plug negative 3 in here, this first term's going to drop out. Plug negative 3 in here, the second term drops out because that gives 0. And negative 3 in here and here, so you've got negative 3 and then negative 3 minus 3, negative 6. So negative 3 times negative 6, 18c. So this is going to be 18c. And so then divide both sides by 18. So c is going to be equal to negative 9 over 18, which is negative 1/2. So now we can plug those numbers in up here. So our a is the number over x, that's 1/3. So this is a 1/3. And then b is the number over x minus 3 right here. And our b was 1/6. So plus 1/6 over x minus 3. And then c was the number over x plus 3, and that's our negative 1/2. So minus 1/2 over x plus 3 dx. And so now we can just integrate each piece separate. So we can bring this 1/3 on the outside, so we'll have 1/3. So the integral of 1/3 over x is 1/3 comes out times the integral of 1 over x dx. And then the integral of this term, so what we're doing is this. We're integrating each term separately with respect to x. So the integral of this middle term, the 1/6 will factor out, so plus 1/6 comes out. And then we've got integral 1 over x minus 3 dx. And then the last term, when we integrate there, negative 1/2 comes out, so minus 1/2. And then we're integrating 1 over x plus 3 is left. And dx. My 3 is kind of scrunched in there. There we go. And then now these are not hard integrals. Okay, the integral of 1 over x is ln x. So this is going to be 1/3 natural log. And that's absolute value of x, right? And then plus 1/6. And now the integral of 1 over x minus 3, well, the derivative of x minus 3 is 1, so this looks like g prime over g. And remember that if you integrate g prime of x over g of x, derivative of the function over the function with respect to x, remember you get the natural log of the absolute value of that bottom function, g of x. And then plus a constant, because it's improper integral. So we're going to get, this is going to be natural log absolute x minus 3. And then minus 1/2. And then this is the same way. Derivative of x plus 3 is 1, so that looks like this too, g prime over g. So we get log of the bottom, absolute value, so absolute x plus 3. And then plus a constant. And we got it. So that one is done. All right, so let's look at this next one. So here we got a definite integral, and we're integrating tangents and secants, so that's a trig integral, which is a special type of u substitution. So remember, what we want to do is we want to look for what is the du first, find the du. And we don't have two secants here, or an even number of secants, so secant squared can't be our du. Okay, so that means that our du is going to have to be secant tangent. So we need to break a tangent off of here. So we're going to write this as integral from 0 to pi over 3. And then we'll have tan squared x. I'll break off one of those tangents and put it with the secant x. So times secant x tan x dx. And there's going to be our du, because remember the derivative of secant x is secant tangent. Okay, so that means that our u is going to equal secant of x. Whoops, not squared, just secant x. There we go. And so then we got to write tangent squared in terms of secant. Okay, because you got to have everything in secants. So this will be integral 0 to pi over 3. And then remember, tangent squared is secant squared minus 1. So this is a secant squared minus 1. Secant squared x minus 1. And so what we're really integrating then is secant squared x minus 1, that quantity, times our secant x tan x dx. So here's our du. And then if u is secant, then this is going to be u squared and then minus 1. So u squared minus 1. So now we'll go ahead and change everything over to u. So this will be integral of u squared minus 1 du. And we've got to change those limits of integration, the 0 and the pi over 3 over. So if x is equal to 0, then we've got to plug that into our u equation. Then u is going to be the secant of 0. Okay, right? We're plugging x equals 0 in here. Remember, secant's 1 over cosine, and cosine of 0 is 1. So this is 1 over 1, which is 1. So that lower limit's going to be 1. And then we're going up to pi over 3. So if x equals pi over 3, then our u is going to be secant of pi over 3. Which is going to be 1 over cosine of pi over 3. Remember, secant's reciprocal of cosine. And then recall that the cosine of pi over 3 is, let's see, what is cosine of pi over 3 again? 1/2, I believe. Pi over 3 is up here. X coordinate 1/2, y coordinate root 3 over 2. Yeah, cosine is 1/2, and sine is going to be root 3 over 2. So that's from unit circle. So this is a 1/2 in the bottom, 1 over 1/2, which is 2. So this is going to be 1 to 2. So now it's an easy integral on u. It's just power rule. Raise the exponent, divide by the new exponent. So this is going to be u cubed over 3 minus antiderivative of 1 is u, and then this is a definite integral from 1 to 2. So plug in 2, plug in 1, and subtract. So we plug in our 2, that's going to be 2 cubed over 3 minus 2. And we are subtracting off, plug in the 1, so 1 cubed is 1 over 3 minus 1. And if you do the calculator work there, you will get 4/3. And I'll leave the calculator work to you. So let's see, up next here, it looks like we are integrating powers times an exponential. And now notice in this problem, I've got a choice here. And the reason I've got a choice is because this first one is a tougher problem. This is a 2-method problem. The second one, though, is a single method problem. I see a power here times an exponential, which is your hint that, oh, we should use integration by parts there. But this one, same thing, integration by parts, but it's parts along with another method. So, and what I found in the past is that sometimes when I just give the harder problem and no choice, students would totally blank out on this and they get 0 points. So instead what I said was, well, I don't want people to get 0 points on a whole problem because that's going to blow their average. So I would do an easier version. And you should know how to do this one, but just in case you blank out here, you can try the easier version. And you get done, if you feel confident on that, well then take a stab at this, and then I'll grade them both and you get the higher of either one. So, but notice that this one is only worth 9 points instead of 12 like the rest of them, so you kind of get docked a little bit here for difficulty. Because I'm not going to put just all one-step problems on there. You should know how to do some 2-method problems. And the ones you've done so far have all been 1 method. So let's tackle this one here, and then we'll come back over and tackle this one. So like I said here, we see a power here times an exponential, so that's telling us integration by parts. And so we need to pick a u and a dv. And remember, you want to pick u so that it's got a simpler derivative, and dv so that's easy to integrate. And usually if you've got power in there, then u is going to include the power. So let's let u be the 3x, because that's going to differentiate, and it's going to give us 3, which is simpler. And we'll let the dv be e to the 5x. And that's not hard to integrate. Remember, if you differentiate e to the 5x, you get e to the 5x times 5. When you integrate, which is what you need to do to get to the v, you're going to get e to the 5x and then divide by the 5. You actually do a little u substitution to show that. But what I'm doing there is I am using an integral formula that if you integrate e to a number times x, e to the ax dx, that you're going to get 1 over a times e to the ax, and then plus a constant. So, and you can show this using the u substitution. And then our du here is going to be 3 dx. And then remember, we do uv minus the integral of v du. So it's diagonal and to the left. So this integral here is going to be equal to uv. So that's going to be 3x times 1/5 e to the 5x. So that's going to be 3/5 x e to the 5x, if you'll let me simplify that in the same step, minus the integral of v du. So this is my uv minus integral v du, and this is my integral of u dv. And so our v du is this product here, which is just going to be 3/5 e to the 5x dx. And then we're almost there. We can take this 3/5, pull it out in the front of that integral, and then we're just integrating the e to the 5x again, which we already did up here. From here to here, we did an integration. So this is now going to be 3/5 x e to the 5x minus that 3/5 will come out. And then you integrate e to the 5x, you're going to get e to the 5x, and then times another 1/5. And then plus c, because it's a indefinite integral. And then you don't have to simplify anything on the test, but we'll go ahead here. 3/5 x e to the 5x. And then this will be 3/25 multiplying straight across the top and the bottom. E to the 5x, and then plus a constant because it's indefinite. So that one is done. Okay, just one method, integration by parts. But this one over here, notice that I mean, if you differentiate the x to the 9th there, you're going to get 9x to the 8th, which is easier. But if you pick the e to the x to the 5th as the part to integrate, how do you integrate e to the x to the 5th? So in other words, if you start out saying, don't write this yet. Okay, I'm going to do my u and my dv. And if I say, well, u is going to be 2x to the 9th, and my dv is going to be the e to the x to the 5th, which is what you usually like to do with integration by parts. You let the u be the part that's got the power in it. Well, we don't know how to integrate this because it's e to a function, okay, and it's not just a linear function. We could do 5 times x because it's just a number times x. We're using this formula. But this is x to the 5th power. That's a function inside a function. That's a chain rule. We need some extra work there. That's not going to work for us. So what we want to do is we want to do a simplifying u substitution first. So let's go ahead and rewrite this integral. And see, what we would like is, since this is an x to the 5th, we'd like to have an x to the 4th out in front. So let's break off an x to the 4th out of that 2x to the 9th. In fact, let's see, we actually could bring that 2 out in front here. So let's go ahead and do that. And then this will be integral, and break the x to the 9th up as x to the 5th times x to the 4th, and then times e to the x to the 5th dx. So now if I let u equal x to the 5th, then here's my du. Okay, almost. Du would be 5x to the 4th. So we can do a simplifying u substitution. That'll simplify this, and then what's left we can do integration by parts on. So our u substitution here, and let's use a different variable because we're going to use u and dv when we do the integration by parts. Let's call it w, and let's let w equal x to the 5th. And in that case, dw is going to equal 5x to the 4th dx, and we've got the x to the 4th dx. Let's go ahead and multiply by a 5 inside the integral, and then we'll divide by 5 on the outside to compensate. So all we did was multiply by 1. Then these two pieces here together, that is our dw, and then this is our w. So now we've got 2/5 out in front, and this will be integral x to the 5th right there, that's w, so this is w out in front. 5x to the 4th dx, that's our dw, and then e to the x to the 5th, that x to the 5th is also w, so this will just be e to the w. And now it's simplified, and it's all set up to do integration by parts. So now we'll do our u and our dv here. So u and dv, and we'll let u be w because that's going to definitely simplify when you differentiate it. And dv is going to be our e to the w, which is definitely easy to integrate. So actually be with the dw. So then du is going to equal dw, and then v, we integrate e to the w, we get e to the w. So we're going to do uv minus integral of v du. So w e to the w minus the integral of v du, which is just e to the w dw. So again, this up here, this is that's our u dv, that's our integral of u dv, and this is our u v minus integral v du. So now we're almost there. So w e to the w, we keep that. And then the integral of e to the w is just e to the w. And it's indefinite, so add our constant. And then the last thing, don't forget to change back to x, right? W is x to the 5th. So you got to put it back in the original variable. So this w is x to the 5th times e to the w is x to the 5th minus another e to the x to the 5th and plus c. And now we got it. Okay, two method. So you can expect some two method problems. But I will give you some choices in the test to try and help, so if you blank out on a problem. Okay, number 10, I look at this here and I see that square root right away, and I also see perfect squares underneath there. So that 1 minus 4x squared. So I am thinking trig substitution. And the trig substitution that this looks like is, it looks like 1 minus sine squared. 1 minus sine squared theta. And notice that the 1's already match up. So our substitution here is that the 4x squared has to be sine squared. Okay, so 4x squared then has to equal our sine squared theta. And then take square roots on both sides. So 2x will equal sine theta. And then x is going to be 1/2 sine theta. So there's our substitution. And then dx, the derivative then, is going to be 1/2 derivative of sine is cosine. So cosine theta, d theta. And now we want to change our whole integral over. So the 1 minus 4x squared we know is 1 minus sine squared theta. We set it up that way. So integral in the bottom, we already know what we're getting here. It's 1 minus sine squared theta. And then on the top we've got that 3x squared, so 3, and then our x is 1/2 sine theta. So we're going to have a 1/2 and sine theta, and that whole thing gets squared. And then our dx is 1/2 cosine theta, so times 1/2 cosine theta. So then 1 minus sine squared down here is cosine squared theta, and then that's going to be underneath the square root. So we're going to get then integral, we got that 3. Let's square the 1/2, square the sine squared. So if you square 1/2, you get 1/4. 1/2 times 1/2. Square the sine, you get sine squared theta, and then we've got that 1/2 cosine theta out on the end, d theta. And then down in the denominator, we've got square root of cosine squared. So the square root and the square are going to cancel each other out. We're just going to have a cosine theta left there. Right? It's square root of cosine squared. So the square and the square root are going to cancel out. So that's just going to leave us with cosine. So I'll just do a little reminder there. And then these cosines cancel, so that's pretty cool. That makes things a little bit easier. And now let's go ahead and pull all our constants out in front. So we got 1/4 times 1/2 is 1/8 times a 3, so that will be a 3/8 coming out in front. And then what's left to integrate is just the sine squared theta d theta. So now it's reduced to a trig integral. So trig substitution gave us a trig integral, and that's usually what happens. And it's even powers in both sine and cosine because there's no cosine, so it's 0 power. So remember with even powers on everything that you have to use the half angle identities. So we want to trade out that, that sine squared for 1/2 times 1 minus cosine of 2 theta d theta. So this is the half angle identity here for sine squared. So that sine squared is right there. And now let's see, let's go ahead and take this 1/2 and bring it out front with the 3/8. So that's going to give us 3/16. And now we can go ahead and integrate. So the integral of 1 with respect to theta is just going to be theta minus, and then the antiderivative of cosine 2 theta is sine 2 theta almost. If you were differentiating the cosine 2 theta, you'd multiply by the derivative of the inside. That 2, when you integrate, you're going to divide by it. So 1/2 sine 2 theta. This is an indefinite integral. It'll be a plus c on the end. So we've integrated everything. Now we need to change it back to our original variable, which was x. And that's where we're going to use the triangle. But first, let's sub out this sine 2 theta, do a double angle identity. So we got this 3/16 out in front, and then theta, and then minus 1/2, and then sine of 2 theta, the double angle identity is that that's equal to 2 sine theta cosine theta. And then plus c. And then these 2's cancel. So now we just need to know, well, theta we know is going to be inverse sine of 2x, if we take inverse sine on both sides here. And we need sine theta and cosine theta. Well, sine theta we already know is 2x, but we need that cosine theta. So here's where we're going to go ahead and use the triangle here. Okay, so do our triangle to reverse the substitution. So there's our angle theta. And what we know here is that sine theta is 2x. So sine theta is equal to 2x. And we'll write that as 2x over 1. And sine is opposite over hypotenuse. So opposite of the 2 theta is opposite of the theta is our 2x, and hypotenuse is 1. So then this side is going to be the square root of hypotenuse squared, 1 squared is 1, minus the leg squared, 2x quantity squared. And 2x times 2x is 4x squared, so that side is root 1 minus 4x squared. And then check this out. Root 1 minus 4x squared is right here. It's the denominator of the original integral. Okay, that always happens. If you don't see part of that integral show up in your triangle, and you did something wrong, and you need to check your work. Okay, so we're almost done here. So 3/16. Okay, and then theta, well, sine theta is 2x. So theta is the angle, and when you take the sine of it, you get 2x. So theta is the inverse sine of 2x. That's what inverse sine means. And then minus sine of theta, we already know is 2x right there. And then times cosine of theta. Well, here's our theta. Cosine is adjacent over hypotenuse. So that's going to be times root 1 minus 4x squared over 1. And we don't need to write the over 1. So it's just root 1 minus 4x squared. And close up our parentheses, plus c. And ta-da! We've got it. And we have to say ta-da on that one because this was a lot of work. Okay. Alright, so trig substitutions. Yeah, trig substitutions are usually a lot of work. But that's okay. We are up to the challenge. Yeah, you're probably saying, no, I'm not up to the challenge. Okay, well, you're going to have to be up to the challenge by the time the test comes around, so work on it. All right, I look at this example and I see that square root, but there's no square under it. So I'm thinking rationalizing u substitution. So in here we want to do u equals the square root of x plus 3. And then remember with the rationalizing substitutions, what you do is you've got to take up that dx in terms of u's also. So what you want to do is here is square both sides. So u squared then is equal to x plus 3. And then take the differential of both sides. So the differential of u squared is 2u du. And then the differential of x plus 3, well, differential of x is 1. Differential of 3 is 0. And then times dx. Okay, so your dx is 2u du. And then we need to know what x minus 1 is. Okay, so here, if we solve this for x, bring the 3 over as a negative, then u squared minus 3 is going to equal x. So then that means that wherever we see an x, we can put in u squared minus 3. So now let's go ahead and change this guy over. So this will now be integral on the top, that's our u, On the bottom here, x is u squared minus 3. So we've got a u squared minus 3. And then minus 1. And then our dx is 2u du. So times 2u du. So let's do a little bit of simplifying. So then this is going to be integral. On the top we've got 2u times u is going to be 2u squared. And then on the bottom we've got u squared minus 3 minus 1. U squared minus 4 du. Alright, so we changed it over. We got rid of our radical. So that's what the rationalizing did for us. And now this is polynomial over polynomial. That is telling us partial fractions. We got to do partial fraction decomposition. So notice here that the power in the numerator is the same as the power in the denominator. So we've got to do a little bit of long dividing here. Okay, so let's do a little long division here. So we want to divide the denominator into the numerator and get that quotient here. So u squared minus 4, we are dividing that into 2u squared. So we divide the first terms there. So 2u squared divided by u squared is equal to 2. And let's do a plus 0 underneath the square root. So we've got the constant column. So then that 2 is going to go here. And then you multiply out in front, put that down underneath. So this multiplies out in front, put that down underneath, and then subtract. So 2 times u squared is 2u squared. 2 times negative 4 is negative 8. And we are subtracting here, so we're going to change the signs, minus, plus, and then add. So these guys are going to cancel out. 0 plus 8 is 8. And our remainder now has a exponent that is less than u squared. So remainder 8, remember we would write that as, you can do plus remainder over divisor. So 8 over u squared minus 4. So now this is just saying that we're going to integrate 2 plus 8 over u squared minus 4 du. So this part is easy to integrate. That's just 2u. And then this part, that's what we got to do the partial fractions on. So notice that this guy factors into u plus 2 times u minus 2. So when we do our partial fractions, let's go ahead and do that down here underneath. So let's see, we've got a 8 over u squared. Well, let me go ahead and use the factored form. U plus 2, u minus 2. That is going to equal the decomposition. We're going to have a u plus term on the bottom, u plus 2 term, and there will be a number on top, so a over u plus 2. And then we're going to have another term with u minus 2 in the bottom, so distinct linear factors, and then a number b on top. And then we're going to multiply through by this LCD on both sides. So multiply on the left by u plus 2 and u minus 2. And then multiply on the right also by u plus 2, u minus 2. That whole thing. So this whole thing is going to get multiplied in times each piece. So on the left-hand side, u plus 2, u minus 2, they just cancel. We get 8. On the right-hand side, u plus 2, u minus 2 comes in times this first term. The u plus 2's cancel, so the a is left, and then the u minus 2 is left. So a times u minus 2 plus, when we multiply this whole thing in times this term, the u minus 2's cancel. We're left with the b and the u plus 2. So b times u plus 2 And then you pick numbers to plug in for u. So, and then the nice numbers to pick are going to be -2 and +2, the zeros for the denominator. So if u equals -2, your left-hand side is 8. And let's see, this is going to be -2 minus 2 is -4, so -4a. And then here, -2 plus 2, that one drops out, so that's nice. So then a is going to be 8 divided by -4, which is -2. And then plug in u equals 2, which is the 0 for the denominator here. We get 8 on the left-hand side right here. On the right-hand side, 2 minus 2, this term drops out now, and 2 plus 2 is 4. So 8 equals 4b. And so divide both sides by 4, b equals 2. So it's -2 over u plus 2 and +2 over u minus 2. So now this is integral of 2. And then it's -2 over the u plus 2. And then plus 2 over u minus 2. And we are integrating that guy with respect to u. Okay, so now this isn't too bad. The integral of 2 is just going to be 2u minus, and then 2 will bring out in front. We integrate term by term. So if we pull that 2 out, or pull the -2 out, then we'll have 1 over u plus 2. That's a log. That looks like g prime over g. The derivative of u plus 2 is 1. So we got the function on the bottom and derivative on the top. Remember that if you integrate g prime over g, remember you get the natural log of absolute value of g, natural log of absolute value of the bottom. So this is going to be ln absolute u plus 2, and then plus, take this 2, pull it out in front, and then we'll have 1 over u minus 2. That antiderivative is going to be natural log absolute u minus 2. And then plus c, plus constant, because this is an indefinite integral. So plus c. And then we're almost done. We just have to plug back in our u. Our u is right here. It's root x plus 3. So this will be 2 root x plus 3. And then minus 2 natural log absolute root x plus 3 plus 2 outside the root. And then plus 2 natural log absolute root x plus 3, and then minus 2 outside the root, close it up, plus c, and we got it. So that one was also actually 2 methods, because we did the rationalizing substitution, and then rationalizing substitutions, they almost always will end up in a partial fraction. So there'll be a couple problems. They're going to be 2 method, and then the rest will be 1 method. All right, next up, looks like we've got an indefinite integral here. And let's see, the zeros for the denominator here, we've got indefinite because it's got an infinite limit of integration here, going out to infinity. And then the zeros for the denominator there, 3x squared minus 1, that is equal to 0 when bring the 1 over, 3x squared equals 1, x squared is equal 1/3, and then take square roots. X is going to equal positive and negative square root. Root 1 on top is 1, and root 3 on the bottom. So 1 plus and minus 1 over root 3, which is less than 1. Okay, so that's not inside the interval from 1 to infinity. So this is only improper at the one end. So you want to check and make sure it's not improper at both ends, because that is possible. If it's improper at both ends, remember you have to break it up. Okay, break it up into two pieces and then look at one of the pieces, or one piece at a time. So this one we're going to do a limit, and we are going to integrate from 1 up to b, and we're going to let b go to infinity. So that's the first thing that you do when you got an improper integral, is get that limit in there. X over 3x squared minus 1 dx. And next, let's see, I look at this and I see that x squared on the bottom and an x on the top, so it looks like we need to do a u substitution to help in evaluating here. So why don't we let u equal the whole bottom there, 3x squared minus 1, and so then du is going to be 6x dx. And let's see, we got the x dx up here, so why don't we multiply by 6 there and then compensate on the outside of the integral with a 1/6. So this will now be limit as b goes to infinity, and I got a 1/6. And now integral 6x dx right there, that is our du. So du on the top, and then the bottom is just u, so du over u, and then we got to change these limits of integration over to u also. So if you plug a 1 in here for x, so x equals 1, then our u is going to equal 3 times 1 minus 1, which is 2, so this will be 2. And then if x equals b, well, you plug that in here, you're going to get 3b squared minus 1. So our upper limit is 3b squared minus 1. But now our integral is a lot easier, okay? Because the integral of 1 over u du is just natural log. So this is now going to be limit as b goes to infinity. And got that 1/6 out in front, don't forget him. And now this is going to be natural log of absolute value at the bottom, absolute value of u, and that natural log is going to get evaluated from 2 up to 3b squared minus 1. So now we plug in those two guys and subtract. So now this is going to be limit b goes to infinity, 1/6. And now plug in the 3b squared minus 1, so this is going to be natural log absolute value 3b squared minus 1 minus natural log, plug in the 2 for u, natural log of 2. And then we go ahead and look at what happens as b goes to infinity. So as b goes to infinity, the 3b squared becomes infinite minus 1. That's still, this inside here is approaching infinity. And if you take the log of something that's approaching infinity, then that's going to go to infinity. So this whole piece also approaches infinity. And then log of 2, or log of absolute value of 2, we really don't need the absolute values there because 2 is positive. That's just a number. So infinity minus a number is infinity times a 1/6, still infinity. So this guy diverges. Okay, so remember, in infinite area is what that's saying. Diverges, and you need to tell me if it diverges. If you get a number here, you don't need to say anything else, but there's different ways to diverge here. So you have to interpret the answer to your limit. Now, just a note here, I could change this to a problem where, you know, maybe I'll make the function you integrate is easier, but then maybe you have to break it up into two pieces. So for example, if this integral would have gone, so this is total separate problem here, separate example, just to give an idea how I might change things. If this would have been integral from 0 to infinity of x over 3x squared minus 1. Then what you do is you've got, that includes one of these zeros for the denominator, the 1 over root 3, and you'd have to break this integral up at the 0 for the denominator. So you break it up into two pieces, 0 to 1 over square root of 3 plus integral 1 over square root of 3 to infinity. And then you would evaluate both pieces. Now this one is only improper at the upper limit, and this one, actually this one is improper at both ends. This is a 0 for the denominator and this is infinity. So you probably would want to evaluate this integral first. If it's infinite, then the whole thing will diverge, you're done. If you have to evaluate this one, you'd have to break it up farther. So I probably wouldn't do that, but actually I could, I might do something like this. Let's back it up. Let me change my example here a little bit. I could do, for example, instead of 0 to infinity, I could do from 1 over root 3 to infinity, where it's improper at this end because 0 for the denominator, it's improper here because infinitely long interval. So if that happens, you have to break it up at an intermediate point. So you could do from like 1 over root 3 to 1 plus the integral from 1 to infinity. Same function inside. This piece is only improper at the lower limit. This piece is only improper at the upper limit. Then you can analyze each piece separately. And so if you did this piece, you'd get infinity, it would diverge, so then the whole thing would diverge. So this piece here, we already showed that this is infinity, so this whole integral diverges. Okay, so you wouldn't even have to do anything with this part. Okay. So again, I can change the question slightly, and I will. All right, last problem. And this practice exam, again, is longer than the actual exam. Okay, so I'm trying to give you more practice than you need. You can't get too much practice. So we want to find an upper bound or an estimate on the absolute error from integrating 0 to 1 e to the 4x dx using the trapezoid rule with 20 rectangles. And so here's our error formula for the trapezoid rule. So remember that k sub 2, that is a bound on the second derivative. So the first thing that you want to do in trying to estimate the error, remember this E stands for error, T is trapezoid, N is the number of intervals here, and that's 20. So N is equal to 20 to start off with. And then our function, our f of x here, is the function we're integrating, e to the 4x. And then a and b are limits of integration. A is 0 here and b is 1. So a is 0 and b is equal to 1. So that's our given information. First thing you want to do is find that number k sub 2. So take two derivatives. So the 2 means take two derivatives here. So this will be e to the 4x, and then we'll have to multiply by 4, derivative of the inside function. And then take another derivative. So we get e to the 4x times 4 times the 4 that's already out in front, so 16 e to the 4x. And then the number k2, that number is an overestimate of the absolute value of the second derivative. Okay, now our second derivative, our x is going from 0 to 1, so this x is positive, so e to any number is positive times 16 is positive, okay? So this is all positive, so we really don't have, we really don't need the extra value, the absolute values in there. But yeah, remember that number k sub 2, if we go back to our formula sheet here, let's see here, numerical integration here. There we go. The absolute value of the second derivative has to be less than that number k sub 2. So that's saying that k sub 2 is an overestimate of the absolute value of the second derivative. Okay, so we want this k sub 2 to be a number that's bigger than 16 e to the 4x. I'm going to go ahead and put the absolute values around here just to remind us that once you get that second derivative, you have to take absolute value. But absolute value of 16 e to the 4x is just 16 e to the 4x. It is positive. Now, if you graph this function on your calculator, and let's actually do that here real quick from 0 to 1. So here I went to the TI-84. I've already put in the e to the 2x. And then what you want to do is you want to go to Window and set your x min to be 0 and set your x max to be 1. Okay, and then it never goes below 0, so let's go ahead and let's set our y min to be 0, and our y max, it might end up being higher. Let's go ahead and graph and see what happens. So we graph here, and so this is our exponential function between 0 and 1, and it goes off the right of the screen. So that means that we have to change our window, increase the y max here. So that's why we increase that to 20 and graph again. Okay, so at 1 here, it's not going off the top of the screen, it's going off the right, so we're okay. Yeah, I'm sorry, we could actually left that at 10. That's fine. It's only when you're going off the top of the screen that you want to increase your vertical scale here. So what we see here is on the interval from 0 to 1, this function is increasing from left to right. So that means that the maximum value of the function on the interval 0 to 1 is at the right value, which is at 1. Okay, so this k2 is actually going to be equal to 16 times e to the 4 times 1. Okay, because this function between 0 and 1 looks like this, and so what we want to do is we can use the overestimate. It's just going to be the max value of the function. Okay, so that's our k sub 2. Okay, and so 16 e to the 4th, if you plug that into your calculator, that is approximately 873.6. Oh, wait a minute here. Go back to our function. We did e to the 2x. I want to do 16 e to the 4x. What am I doing? 16 e to the 4x. There we go. And if we graph that, then it's not even on the screen as we're graphing it. Okay, so we go to our window here, and we've got to increase our y max. That's why I was thinking I had to increase our y max, because we do. So let's try increasing that y max to 100, and now graph again, and we see that the function's going off the top of the screen. We want it to go off the right, so we're not big enough yet. So let's go back to our window here, and let's try 500, and let's graph again, and that's still going off the top of the screen. Okay, so if you go to window here, let's go ahead and change this to 1000 and graph again. And now we see that it is going off the right of the screen. So we know that our case of 2 is, less than 1,000, the best value for case of 2. And then I plugged in 1, so that's going to be the value at the right-hand endpoint, and that's approximately 873.6. Now, you can also estimate this with the trace function on your calculator. So if you use trace here and you just go to the right until you're at x equals 1, then that's also going to be an estimate for your max. Okay, so let's say it's 1.01. So at x equal 1, 873.57, and we used 873.6. So we rounded up the decimal place. Okay, so we know that this is bigger than all of the f double prime values. This is our f double prime function. Okay, so you can do that on the calculator, or you can do it by looking at the graph and then plugging in the highest endpoint. So now we can go ahead and plug into this formula. So let's go ahead and bring that guy down here. Okay, so then to finish up, we're going to go ahead and plug in our values. So our case of 2 there is 873.6. And then our b minus a cubed, b is 1, minus a is 0, that gets cubed. And then we're dividing by 12 times n squared, which is n is 20, so 12 times 20 squared. And then if you plug this into the calculator, you'll get approximately 0.182. So if we carry that out to 3 decimal places, so that's our maximum error. That's our estimate for the absolute error, is that 0.182. So the tough part is getting this number here. Okay. If we wanted a rough overestimate, we could have just used 900. Okay. There's no one absolute correct number. Okay, but this one is close. It's within 1 decimal place. All right. So that wraps it up. But you need more practice. Okay, you need to take one of the other practice exams with no study aids and see where you need work. And then I've also included another practice exam. So you got 3 practice exams, 1 to work through and review the material, and then 2 more to practice your problems. So I encourage you to work through all of those practice problems, and then even try extra practice problems on the ones that you are having trouble with. And again, the other 2 you want to try and take with no study aids, because then you're going to know which ones you really need help on.